Okay, let's see. All right. So yeah, thanks very much. Thanks to the organizers for putting this on, and very much for the opportunity to speak. I'm going to talk about something that me and my friend Nestor Diaz Morera have been working on for the past several months, sort of on and off. We started talking last fall about a project we might want to work on, and I suggested this as something that I thought would be sort of easy and quick, and a chance to learn some interesting mathematics a little bit better. It has turned out to be not quite as easy and quick as we thought, of course, but we still have something that is a little bit interesting to say, and I think there's interesting problems here that I wanted to draw folks' attention to. So we're going to start with this definition of shellability. It's come up a couple times in the summer school, but I guess hasn't been explicitly laid out and defined. So we'll start there, and it comes from the study of simplicial complexes. Uh-oh. Maybe I forgot to change that on my computer. Okay, here's what it says. If you have a pure simplicial complex, meaning all the maximal faces have the same dimension, if you can order those faces in a way such that at each step, the new face you're bringing in, the way it intersects with everything before it, is a union of maximal proper faces of the new thing, so codimension 1 faces, then that's what it means to be shellable. So this takes a little bit of getting used to, I think, the first couple times you see it. Doesn't seem exactly natural, but really what you're doing is like, okay, you start with one of your simplices, and you just start gluing things on so that you're preserving the property of being homeomorphic to a ball, right? So like you could start for this complex here with just one of these triangles over on the left here. You glue on another triangle, okay, still a ball. Another triangle, still a ball. Last triangle, still a ball. And that's what it means to be shellable. So you can see sort of what this means is basically if you're bringing in any new vertices to your shellable complex, at each step you can only be bringing in at most one new thing. And so we saw something that wasn't shellable that looked sort of similar to this or had this as a subcomplex. And the problem here is, well, there's only two possible orders here, and check each one. You can't get around the fact that you have to introduce two new vertices either way you order it. So this is kind of has the flavor of a search problem, and it was actually proven recently that shellability, deciding shellability, is NP complete. But there are ways to establish shellability for simplicial complexes, or what we're going to be more concerned with, posets that make it so that you can avoid a lot of that search procedure. So I've drawn posets here that correspond to these simplicial complexes, and there are dictionaries between posets and simplicial complexes. From a poset P, you take what's called the order complex, which I'll explain in a second. You can get back a poset from a simplicial complex by taking what's called the face poset. I'm not really concerned with that direction, and these maps are not exactly inverses, but we did see over on this other side from simplicial complexes, we have this Stanley-Reasoner correspondence with square-free monomial ideals. And so what we're doing here, we take a poset P, and you look at all of its maximal saturated chains, and those just become simplices. So like 1, 2, 3, that becomes this triangle 1, 2, 3 over here. 1, 5, 3 is this triangle down on the bottom, and so on. And you can do operations on your posets like adding a top or a bottom element, and shellability is preserved, we see here. So I've got this other related poset where with the nodes suggestively labeled, and I've got now this octahedron formed by the attachment of these 4 tetrahedra that is once again shellable. And now what you see, you recognize this poset over here, not shellable because again it has sort of like this hinge between the 2 tetrahedra that there's just no way to get around. All right. So just to set up a little bit of poset terminology, right, we know what it means to be bounded. It just means there's a unique maximal and minimal element. Covering relations is y is above x, and there's nothing in between. A chain is saturated if it's formed totally of covering relations. Graded means like graded module, but the right way to say it is all maximal chains have the same length. And in this case, we have a length function, which basically assigns the length of a chain from a minimal element up to where you're at. And so all of the posets we're going to be looking at are going to be graded because they come from a geometric context where the grading is essentially dimension, but length doesn't have to be exactly equal to dimension. And now we can just say that a poset is shellable if its order complex is shellable. All right. And so one of the main ways to establish shellability for a poset is to talk about this notion of lexicographic shellability, which comes from work of Bjorner. And I guess this is one thing that I guess came up in the summer school. Right? If we know our poset is lexicographically shellable, we know the simplicial complex is shellable, and so we know on the other side the associated ring is Cohen-Macaulay. I found a paper of Buklowski that attributed this to Folkman from '66. Didn't check that, but correct me if I'm wrong on that. In any case, let me define what this lexicographic shellability thing is. So you take the set of all edges in your poset. Right? You've got these covering relations. And an edge labeling is just a map on those covering relations to another poset lambda, which most often you take to just be integers or natural numbers or some product of those with the total ordering of lexicographic ordering. And we can say that a chain is increasing if then you read up the side of the chain, and we just want the labels on those chains to go in increasing order or weakly increasing order. And so this property EL shellability just says that there is some labeling such that in each closed interval there's a unique rising maximal chain, and also the word associated to that chain has to be lexicographically smallest. All right, so a brief overview of the relationships between shellability and Bruhat order. It was known since, I guess, almost right after Bjorner's paper that the symmetric group Bruhat order is EL shellable, proved by Edelman. Proctor extended this to all classical Coxeter groups. And then shortly thereafter, Bjorner and Wax introduced a related but slightly different notion called CL shellability, which allowed them to show that any Coxeter group or any quotient of a Coxeter group by a parabolic subgroup gives you a shellable Bruhat order. And so it's interesting to note that this was actually used to show that the coordinate rings of Schubert varieties were arithmetically Cohen-Macaulay, I guess. In the case of Gmod, a maximal parabolic in work of Lakshmi Rai and De Concini, but it was a different kind of degeneration, which I guess may be called Hodge degeneration. On these algebras with straightening laws, things called Doset algebras or something like that. Okay, so this was upgraded a little bit later by Dyer, who introduced this notion of reflection orderings. And so EL shellability is the stronger property. And then this was extended by Inchiti to involutions in Weil groups with the restriction of Bruhat order. In the case where, well, first for the symmetric group and then for all classical Weil groups W. A little bit later, fixed point free involutions in SN were shown to be EL shellable by John, Chernyavsky, and Twelbeck. And one other work I'll mention is Chan showing that the Rook monoid is EL shellable. So Rook monoid, I guess people in here will probably want to think of it as matrix Schubert varieties in square matrices. But I was told to think of this as that the fact that you have an analogous decomposition to the Bruhat decomposition for the algebraic monoid, which consists of all matrices, which showed up in work of Renner in the 1980s. Okay, so symmetric spaces should define what those are. If you have a connected reductive linear algebraic group and an involution from G to G, whose square is the, so that means its square is the identity, you take the homogeneous space G mod K and you call that the symmetric space where K is the fixed point subgroup. And it was a theorem first of Matsuki that these symmetric spaces are examples of spherical varieties, so B acts on them with finitely many orbits, some Borel subgroup of G. And it's a pretty cute fact, if you've never seen it before, that you can think of the usual Bruhat order on the Weil group of your choosing as an example of the study of Borel orbits on a symmetric space. So what that symmetric space is in the example of GLN is you've got this involution, which just, if you take GLN cross GLN and you just swap components, you have the diagonal copy sitting there as the fixed point subgroup. And then you take the quotient of the double product mod the diagonal, and you get a copy of G back. It's acted on by a pair of Borels, and the orbits give you the same double cosets. Their closure relations are the same as the ones we know, which is sort of fundamental to the whole theory. All right, so maybe you want more examples of symmetric varieties. Here's a whole list of them that come from, I guess, Cartan's original classification of symmetric spaces as Riemannian manifolds, sort of refining the classification of semi-simple Lie algebras. And so we've got 3 in type A here. These first 2 that showed up in Zach's talk, or the idea of K orbits on the flag variety, if you spin it around, parametrized by involutions and these fixed point free involutions. And so we already know that these 2 things are shellable from Inchiti and Chan-Chernyavsky, Twelbeck. And so just going down the list seems like the next case to check out would have been this A3 case, GLP plus Q mod GLP cross GLQ, in which case the orbit set is the set of PQ clans that showed up in Anna Wygant's talk. So we don't know shellability for anything after these first 2 cases yet, but this seems like the next place to go. And then these ones in green share a common property in that they're symmetric spaces of Hermitian type, which means that they have sort of similar structure that one might be able to exploit once we understand this case to work out shellability for these other cases. Okay, so I don't have to introduce clans too much, thankfully, because we saw them the other day, but I'll just note that I'm going to use the notation which comes from their presentation in a paper of Yamamoto and later in a bunch of work of Weiser, where we have strings in an alphabet which is pluses and minuses, but instead of the arcs and rainbows, I'm just going to use pairs of natural numbers to denote where one starts and one ends. And so there's going to be P minus Q, more pluses than minuses. If a number appears, it appears exactly twice. And so the numbers are just placeholders. We don't care about what they are. We just care about their positions. So here's an example of a 5-4 clan with the arcs drawn in. If you want it there, I'm not going to draw the arcs from now on. And I'll just note that Matsuki and Oshima proved that this was the right set for the set of B orbits in the symmetric space, or once again, K orbits in the flag variety. If you look at this paper also, like where does the term clans come from? It's like very thoroughly anthropomorphic and sort of aggressively heteronormative and binary. And there's like, I think husband and wife and boy and girl are the plus and minuses, but we don't need to do that. I'm just going to call these first numbers, first mates, second mates, pluses and minuses is a good enough name for us, but we will do a little bit more with it in a second. I'll just note that a clan is matchless if it consists only of pluses and minuses. And so this is the first Bruhat poset of a symmetric space where we have a bunch of closed orbits, right? Rather than just a single one. So it's not a bounded poset, and this throws maybe like a wrinkle into how you might go about proving shellability. But it's pretty clearly a shellable space. If you take all the chains, you get these 4 triangles. They glue together. Looks like a ball. So this thing morally should be shellable. In order to actually prove that, you need a pretty good understanding of the covering relations of this poset, which was described in detail in a paper of Weiser, sort of reflecting some structure that comes from just the Bruhat poset on involutions, which was described in Chiti's work. And so what you have is, right, this is sort of an involution with extra data, just pluses and minuses on the fixed points. So if you just forget that data, you get a an involution back. And basically, all of the covering moves that apply to involutions are the same ones you get here. So these are the names from Minchiti's work. And there's just a couple more options because of the pluses and minuses. You can turn plus minus into 1, 1, or minus plus into 1, 1, et cetera, et cetera. They don't follow immediately. So what Weiser does is he shows that, like, if there is a clan that's covered by another clan, there's something in between that is obtained by one of these moves, and then it turns out that the length function on both post sets are the same. So like the covering relations have to be one of these. I guess you also have to prescribe the fact that you're doing this at a rise, which is called free. So this is similar to the case in the symmetric group and involutions. Yes, 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 yeah. All right. So it seemed like a reasonable idea to sort of work with this labeling and see what we could do with it. And you could just blindly apply it. And the first problem that will show up is that, right, because we have more than information than just fixed points, we have pluses and minuses. So two things can happen which give you the same involution, which is this yellow post set up here. So there's like a way around this where you might just introduce another label to keep track of that and say, like, okay, I'm going to prefer minus plus instead of plus minus. But otherwise, these post sets, if you just look at the intervals, right, we're going to want to keep our post sets bounded. So we want unique minimal elements. And as a stepping stone towards proving shellability of the whole thing, we'll just look at the maximal intervals. They're pretty close to post sets of just involutions. The only thing is you've got a couple things deleted. And also, there's extra sort of diamonds you get like this. But having extra diamonds is not really a bad thing when you want shellability, because you really want many ways through the post set in order to be able to bring in new things like one at a time, one after another. So this doesn't seem like a problem, really. There's more of a problem that comes from the fact that if you have long strings of consecutive pluses or consecutive minuses, those the first covering move you can do here to replace those might come later in the sequence. So intuitively, you would want to do some sort of a greedy algorithm that just says, okay, I've got this parameter set, which is strings. I'll just act on them greedily by covering moves, by just taking the first place I can move and moving up the post set that way. If I put my labels on like the symbols where I act, that should be my lexicographically smallest chain, and it should be unique for every interval. And this sort of works, except, right, because you have to act later in the chain than you want to, or sorry, later in the string than you want to, there is not a good way to do this in n to the n with the usual order. So another thing we tried is this EC shellability notion of Kozlov, which seems adapted to this kind of setting, in which you don't have to have like literally increasing labels. You just need to have like a smallest label on every interval of length 2. But what the condition, this EC shellability thing says, is if you're smallest in one interval of length 2 and one above it of length 2, you should be smaller in the larger thing. And so this is an obstruction to that, because the lexicographically smallest chain is this one over on the right. But we have like 2 smallest chains in subintervals here and here. And so Kozlov says that this should be the smallest chain, and this actually breaks. So we tried a couple of other things, like modifications of these orderings, and nothing was working. So to get something that seemed like it would work a little bit better, we retreated not to intervals, but these things called sects. And so I'll tell you what a sect is briefly. You have these projection maps. Because GLP cross GLQ, you think of it as diagonal matrices. It projects into the quotient by a parabolic, so into the Grassmannian. This is an equivariant line bundle. So basically, the projection of every B orbit in the symmetric space goes down to a B orbit in the basement, which is known to be a Schubert cell. Right? And so you can ask which ones project down to which Schubert cells, and describe those combinatorially, and those are the sects. Right? So I've drawn a picture of the sects for the set of all 2, 2 clans over here on the side. And what we can show is actually the sects are EL shellable for any PQ and lambda, which is the partition shape that you fix. I won't say very much about how this works, I guess, but basically what happens is you can associate, if you fix your sect, you can associate to each clan a unique rook placement that lies within a board that is shaped like a partition, right? And you put a poset structure on the rooks in this board shape by saying that they satisfy a collection of rank conditions, northwest rank conditions, if you like. And it works out that the Bruhat order on the symmetric space, if you restrict to a sect, is isomorphic to this poset of rooks with these conditions. And so what we can do then is actually take a labeling scheme that worked for showing shellability of the rook monoid and apply that to the rooks that come from the clans within a sect. And it works out that this does still give you an EL shelling. There's like some extra details to check because of the bytes that are taken out of the board. But everything goes through, and I'll just point out in special cases, you have these clans which are a bunch of minus signs followed by a bunch of plus signs. If there's the same number, you recover shellability of the rook monoid, right? And if it's Q and then P, you get shellability of the Bruhat poset of matrix Schubert varieties thought of as BQ minus cross B plus orbit closures, which I looked and I don't know, correct me if I'm wrong, but I couldn't find this written in the literature. So that's sort of a nice subcase of this more general thing that's happening on the sects. And now, I guess, having gathered some more evidence that this larger thing should be shellable, there's one more idea that we want to check, maybe showing that the full symmetric space is shellable. There are sects of these other Hermitian type symmetric spaces that we could work out that are probably shellable. There's good evidence for this from other work of Chan, Chernyavsky, and Twelbeck. But really, I feel like this is asking for type-independent proofs. I think there's a reason that all of these symmetric spaces should have shellable Bruhat orders. And just, I think this is something that I don't know, I couldn't find about usual Bruhat order on Weil groups, but there's this property called total semi-modularity that seems like it should apply. And I think if you were going to do a type-independent proof, this might be the thing to do. And so I guess I'll leave you with an irresponsible conjecture because I don't feel like it's really my place to make it, but it feels like it should be true, and I guess I'm putting it out there so that somebody can disabuse me of the notion that this is reasonable. But I guess I don't know any reason why Bruhat order on spherical homogeneous spaces shouldn't be shellable in general. And as one piece of scant evidence, just from this paper of Richardson Springer, who first described Bruhat order on symmetric spaces, basically Bruhat order is described as the closure of what you get by completing all diamonds of this form. So if you have a weak order set of edges in this configuration, you fill in all the diamonds. And diamonds are what we want for shellability, so it seems like this should be sort of a property, at least for symmetric spaces, that should be pushing us towards there. So I guess with that, sorry, I went a little bit over. I will thank you for your attention.